Okay, this is part 2 on photoelectron spectroscopy or PES. So this technology is being used to analyze the electron structure of atoms along with other things. But for our purposes, if you're in an advanced placement chemistry class or a general chemistry class at the university level, where the professor is teaching PES, then you may find this video to be useful. So to summarize, the way the instrument works is that it will shine a wavelength of known light on a substance, all right? And we can know precisely the energy of that wavelength because of the relationship that I described in the previous video. So if we know the wavelength of the light that we're using to irradiate or shine on the substance, that light is going to have a certain energy. We can determine the ionization energy of electrons in atoms using PES because we can take and shine light on a substance, and because we know precisely the energy of that of that wavelength, the instrument also is able to measure the kinetic energy of the electron that is leaving the surface of the atom. By taking the difference, we learn the ionization energy of that electron, the energy required to remove an electron completely from an atom. Remember from the previous video that if we know the ionization energy, then we also know the potential energy of that electron, because the ionization energy is equal in magnitude to the potential energy of that electron, but opposite in sign. All right, now, one thing I did neglect to mention in the first video is that PES basically uses two types of light. Either ultraviolet radiation, which goes after the valence electrons of a particular substance, or X-rays. And the X-rays, being higher in energy, are utilized to remove electrons that are closer to the protons, essentially to remove core electrons, whereas the ultraviolet light is used to remove valence electrons. Now, if we want to write the electron configuration for a particular substance, the general format is this. We have the 1s, then we go to the 2s, then the 2p, 3s, 3p. Right in here, we see that energy level 4 overlaps with energy level 3. So we have the system is interrupted. We go to the 4s, and then we have the 3d, and then we would have the 4p. Now, when we write the electron configuration for any given substance, this is the system that we use, and it implies certain things about the energies of these orbitals. For example, energy level 2 appears first before energy level 3. So that means that this series of suborbitals is lower in energy than the suborbitals that are in energy level 3. By the same argument, energy level 1 is lower in energy than the suborbitals in energy level 2, and so on up the chain. We see here that the 4s is overlapped with the 3d, and I want to point out to the viewer right now that although we fill this electron configuration utilizing this model, when we get into period 4 elements, we see that there are some differences in which electrons, the 4s or the 3d, are which of those are actually lower in energy. So the first element that I want to look at here for a PES scan will be calcium. And its configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. All right? We got 18 electrons all the way to here. And then the subsequent second, or the subsequent electrons we have left go into the 4s. So if we were to run a PES experiment on this, we're going to get a scan where the vertical axis is going to give us the relative amounts of electrons, and I'm just going to label this as numbers of electrons. And the horizontal axis gives us the ionization energy, the energy required to remove an electron. And ionization energy will be increasing in this direction. So in a PES experiment of calcium, we would expect to get the following peaks. My artwork is maybe not the best in the world, but it's good enough to make the point. So this position right here is where we would have 2 electrons. So this peak, these 4 peaks are all proportional to the kinds of peaks expected where you would have 2 electrons. And these peaks here would be proportional, areas proportional to where you would have 6 electrons. So this peak is associated with the 1s, this one with the 2s, this one the 2p, this the 3s, the 3p, and then finally the 4s. And the 4s electrons are definitely lower in energy than if we were to try to place them into the 3D shell. So up to calcium, the electron configuration essentially follows the rules. Now what I want to do next is scandium. All right, and scandium has 21 electrons. Now for brevity, what I'm going to do here is, instead of writing the whole configuration, I'm going to start with the 3s. So it's going to be 3s2, 3p6, all right, and then it's going to be 4s2, 3d1, because we have 21 electrons. So this is how you would write this electron configuration if you were asked to do it, for example, on a test. Now, if we look at the scan, here's what it's going to look like. So again, we're going to have numbers of electrons. On the vertical, we have ionization energy increasing to the left. And we would have, here's the 1s, 2s, 2p, 3s, 3p, all right, and then something interesting happens. So what we end up seeing is a peak that's going to look like this, and then a peak that is equivalent to the other peaks that hold 2 electrons. So this is the 2, this is 6, and this is 1. So when we look at the PES scan of scandium, here's what we see. Here's my 1s, here's my 2s, my 2p, my 3s, 3p, and then look what happens. Here's my 3d1, and then my 4s2. So in fact, the 4s2s are higher in potential energy. Higher in potential energy. Higher in potential energy. Lower in ionization energy than the 3d1 electron. All right? Okay, now I think we're going to stop there and we're going to go to a part 3.